start now. Okay. So here is, we have the first session of this year of the TACO seminar. And today we have Alexandra Weinberger of the Institute of Software Technology of Graz. She's doing her PhD there. So thank you, Alexandra. Go ahead.
Thank you. Do you all see my slides now?
Yes, thank you.
Yes. So thank you for the introduction and thanks for coming to this presentation. This is based on joint work with Oswin Eichholzer and Birgit Vogtenhuber, who are from Graz in Austria, same as me, and Alfredo Garcia and Javier Techel from Zaragoza in Spain. As the title suggests, this is all about finding plane subdrawings via generalized twistedness. A bit more precise, we will find plane subdrawings, particularly plane matchings and plane paths in simple drawings of the complete graph. And we use a new type of simple drawings that we call generalized twisted drawings. I will define all these terms and some more things in the first quarter to half of this presentation, and also give you a bit more of an introduction and explain the problem setting, and then talk about these generalized twisted drawings and their properties. And then in the second half of the presentation, we are going to see proof sketches of how they can be used to improve the bound on the size of the biggest plane matching that can be found in any simple drawing of the complete graph, and the length of the longest plane path in any such drawing. So first of all, what are simple drawings? Some of you might have heard about this, but I still want to give a short introduction just in case, and you can see it as a refresher if it's already known to you, starting with a puzzle. I took this puzzle from Schaefer's survey, but it's originally from a magazine in 1913, where it was mentioned that the puzzle itself is much older. And the question there is, given three houses, ABC, how can we connect them with three facilities? One has water, one has gas, one has electricity, such that every house has access to each of these things, so water, gas, and electricity. Now, I hope that most of you will think, oh wait, this is not possible, because basically we can see this as a case 3-3, where the houses are on one side of the bipartition and the facilities on the other. And then the question would be, how can we draw the K33 plane? And this is not possible. We know from Kuratowski's theorem that the K33 is not planar. So this is what I think a solution to this puzzle should be. And it's also mentioned, but actually there is a different solution given. And that is that, oh, we can just connect the water to one of the houses, see here, by going through another house. And with this, avoid crossings. Now, is this a contradiction to Kuratowski's theorem? Of course it's not, because by any definition of drawing that is somehow reasonable, and any definition that is there is never this thing that an edge can go through a vertex. This shouldn't have been allowed. So this is a bit annoying. So let's talk about reasonable definitions of drawings. We will work with simple drawings that are also known as simple topological graphs or good drawings. These are drawings of graphs on the sphere or in the Euclidean plane, where vertices are drawn as disjoint points and edges are continuous arcs connecting the end vertices. Edges are not self-crossing. Also, edges don't pass through other vertices, different from the solution I showed you before. And finally, in simple drawings, any pair of edges may intersect at most once. That can be that they share a common endpoint, or they could cross somewhere in the interior of the edges. What is not allowed is what you can see in the drawings here, that two adjacent edges cross or two edges cross several times. The probably most famous example of simple drawings are straight line drawings. And we are going to see several more examples later in this presentation. But really there are much more of this. It's a very wide and very general class of drawings, and a very natural one that has gained a lot of attention and where there has been a lot of research in the past decades. One of these, the reason that there has been so much interest in these, in addition to them being somehow just a natural way of drawing stuff, is that as long as we are with drawings where edges don't go through other vertices, which we basically always are, any drawing which is crossing minimal is a simple drawing. This is because if we have something like what we can see on the bottom here, then we can just redraw the drawing slightly to get less crossings and still have a drawing of the same graph. It's not always quite as easy as it looks in this minimal example here, but it's always possible. And normally we want this. We want to have as few crossings as possible. And that's also the question of a lot of the open questions that are still there in simple drawings. So many of them have to do with how can we have as few crossings as possible, and what is the number of having few crossings. And despite the fact that there has been a lot of research in this, there is still many open questions. One of the questions, the one that we are going to focus on, also has to do with the fact that we don't like crossings. And this is the question of whether any simple drawing of the complete graph always contain a plain Hamiltonian cycle. It is conjectured that the answer to this question is yes. This has been conjectured already in 1988 and has been verified for graphs of up to 9 vertices, and also proven for some families and special types of simple drawings. But in general, it's still a conjecture. There are two things that would immediately follow from this conjecture. One is that every simple drawing of the complete graph contains a plain Hamiltonian path. And the other is that every simple drawing of the complete graph contains at least n-half disjoint, contains exactly n-half disjoint edges, where disjoint now really means disjoint in the drawing, not only in the graph. So we can't have common endpoints, but we also cannot have any crossings. So actually this conjecture is the same as saying that any simple drawing of the complete graph contains a plain perfect matching. And while these two conjectures are weaker than the original one of the cycle, also these two things are still open. We will look at what do we know about the number of disjoint edges and what do we know about the length of the longest plane path. We know an upper bound, of course, which is that we have a perfect matching and a Hamiltonian path. And as I just showed you, this upper bound is conjectured to be actually the precise value. But the lower bound we know is not yet there. So despite several iterations, we still have a gap between the lower bound and the upper bound for the number of disjoint edges and for the length of the longest plane path. But there has been quite some research in especially the disjoint edges. As you can see here, there have been several years where this number kept being improved and improved. And we have also done this, where we is the co-authors I introduced before to you, Oswin and Alfredo and Javier and Birgit and myself. So we have shown that the number of disjoint edges is at least omega of square root of n, and the number of the length of the longest part is at least log n over log n. And this is what I want to tell you about today. Let me give you a short overview of how the proofs work, and don't worry for now about any terms you might not be familiar with. I will define everything in just a moment. I just want to let you know before we go through all the definitions why we're actually going to need them. So if we want to show you that any simple drawing of the complete graph contains a plane path that's at least this long, then what we show first is that it contains either a plane DRE tree or a C-monotone drawing of the complete graph of a certain size. And if we are in this case of C-monotone drawings, we show that they contain either a generalized twisted drawing of the complete graph or a monotone drawing of the complete graph. And then of all these things, so the plane DRE tree and the monotone drawing and generalized twisted drawing, we will show that they contain a plane path of the length we need. And now you might recognize the generalized twisted drawing name here that I told you about before, and this also in the title. This is because they're going to be important for not only this proof, but also we use them for the proof that any simple drawing of the complete graph contains at least square root of n disjoint edges. There we take a maximally plane matching at first, and we say that either this matching already has the claimed size, or we can find a generalized twisted drawing. And then again, from the generalized twisted drawing, we can say that, all right, in there we have a matching of this size. Now, definitions. Simple drawing is C-monotone, which is short for cyclically monotone, if there is a point such that any ray emanating from that point intersects any edge of the drawing at most once. You can see two examples of how we can draw the K5 C-monotone, but these two are not the only examples. If in the left drawing, instead of drawing the green edge like this, we draw it like this, the short way, then we have yet another way of how to draw the K5 C-monotone. What we cannot do is do it like this, like go in one direction and then turn and come back, because then we would have exactly this double crossing of rays that cross something twice. So this would not be C-monotone. Let's look again at the original examples. They were chosen because both of them are special. The left drawing is special because there we can add a ray that crosses every edge. And we call C-monotone drawings where we can add a ray crossing every edge, generalized twisted drawings. This comes from the term twisted drawings, which is a known family of simple drawings, and generalized twisted drawings are a generalization of them. So that's where the name comes from. And on the right side, we have in a way the opposite. So we can add a ray that does not cross any edge. We call C-monotone drawings where we can add such a ray monotone. This is because this is essentially an X-monotone drawing. We could cut it open at the ray and then just stretch it to get an X-monotone drawing. So these are the two families of simple drawings that we will work with a lot. And I told you before that we use them to say something about plane paths and plane matchings. So we first need to say this about these drawings. Actually, what we are going to show for them is that both of them contain plane Hamiltonian paths. And since they contain plane Hamiltonian paths, they also contain plane perfect matchings. Let's look at monotone drawings first. There, the path is simple. We just go between each two consecutive vertices. And it is known that they cannot cross in monotone drawings. Actually, for monotone drawings, more than that is known. These are one type of simple drawings where we know that they contain a plane Hamiltonian cycle, which I won't prove because we don't need it, but still, if you want to get a feeling for this, I think it's a nice thing to think about this. So here's just some visual hints of how it's normally proven. Now for generalized twisted drawings, we will also show that they contain plane Hamiltonian paths. Unfortunately, there we cannot use the same path we used before, because then we would end up with a lot of crossings. So we need to be a bit more careful here. What we are going to do is to use one of the very nice properties of generalized twisted drawings. And this is that when labeling vertices counterclockwise, like here V1, V2, V3, V4, then the edge V1, V3 cannot cross the edge V2, V4. We can prove this by contradiction. So assume that these edges cross. Then there are essentially, that is up to what we consider strongly isomorphic, two ways of how to draw this crossing. And since we have a complete graph, we know that we still need to be able to draw in the edge V1, V2 and V3, V4. Let's start with V1, V2. We will see that there's only one way, essentially, how to draw this. That's because this edge V1, V2 cannot cross the blue edges you already have drawn because it's adjacent to them and it's a simple drawing. It has to cross the ray R because it's a generalized twisted drawing, and with that, it has to look essentially as it does in these figures. Now we still need to add the edge from V3 to V4, and we'll find that we can't, in fact, because again, it's a simple drawing, so we cannot cross the blue edges here as they're adjacent. We can cross the green edge V1, V2, but only one time, not twice. We have to cross the ray R because it's generalized twisted, and we can't cross any of the rays twice because we are C-monotone. And with these restrictions, there is no way that we could draw this edge. Meaning that in any generalized twisted drawings, these edges V1, V3 and V2, V4 cannot cross. Now we use this for drawings of the complete graph of the n vertices to find our plane Hamiltonian path. The path we pick is that we go from V1 to Vn half plus 1 to V2 to Vn half plus 2 and so on. Then what we get is a set of vertices where pairwise they are all either just two edges are incident to the same vertex. So the edges can't cross because it's a simple drawing, or two edges are of the same form as V1, V3 and V2, V4 were before. So they can't cross because of this property we have just proven. So we have found a plane Hamiltonian path. And it looks a bit like this. We have a zigzag way where we always change sides. Now, this was something general about this generalized twisted drawings and monotone drawings. Let's see how we use them first to show the improved bound on the length of plane paths in simple drawings of the complete graph. What we are going to do as an overview is that we start with a simple drawing of the complete graph and show first that it contains either a C-monotone drawing of the complete graph on D vertices, as long as D is smaller than M, or a plane DRE tree on these D vertices. Where DRE tree is a rooted tree in which every vertex has at most D children. And of DRE trees, it's known and easy to calculate that they always contain paths of length omega of log n over log D. And since our DRE tree is already plane, also our path is plane. If we end up with a C-monotone drawing, then we show first that it contains either a generalized twisted drawing or a monotone drawing of a certain size. And then we also find our plane path because we have just shown before that these two drawings contain plane Hamiltonian paths. So this part of the proof we have already done. Let's look at this part as long as the definitions of C-monotone are still fresh in our mind. So what we want to show is that any C-monotone drawing of the complete graph of D vertices contains either a generalized twisted drawing or a monotone drawing of the complete graph of square root of D vertices. To do this, we use Dilworth's theorem. Dilworth's theorem says that if we have a partially ordered set of at least s minus 1 times t minus 1 plus 1 elements, then it contains a chain of size s or an anti-chain of size t, where a chain is a subset of the partially ordered set in which any two distinct elements are comparable, and an anti-chain is a subset in which any two distinct elements are incomparable. What we need to use Dilworth's theorem on our C-monotone drawings is a partial order. The partial order we define is again based on the same labeling as we had before with counterclockwise V1, V2, and so on. And then we say V1 is smaller than Vj if and only if either I equals j, so we have only one vertex, or I is smaller than j and the edge Vj crosses the ray R. For example, if the edge V1, V2 goes like this, it's comparable because it crosses R, and V1 is smaller than V2 because 1 is smaller than 2. On the other hand, if it were to run like this, it doesn't cross R, so V1 and V2 are incomparable. And we can show that this is indeed a partial order. Once we've shown that it is easy to see that by this definition of two vertices being incomparable if they don't cross R and comparable if they do cross R, that if we have a chain in this partial order, then we actually have a generalized twisted drawing of the complete graph. If we have an anti-chain, it is a monotone drawing. Now, all that is left to do is for us to say, okay, we have the elements and then choose S and T correctly, which we took as square root of n, and then we have exactly what we wanted to show. So this part of the proof we've also talked about, leaving the beginning of how do we find in any simple drawing of the complete graph a C-monotone drawing or a plane geometry. To do that, we take our simple drawing and we take a star in it. The star of a vertex V are all edges adjacent to incident to V. It's plain because it's a simple drawing and all these edges are adjacent. And then we will first add edges to the star until we have a maximally plane drawing. Then we're going to use a very nice theorem that says that any maximal plane subgraph of a simple drawing of the complete graph is biconnected. What this says in our case is that these new edges that we added to the star have to contain a spanning tree. And now we look at the plane substructure we have that consists of the star together with the tree. Then there are two cases with respect to the degree of the vertices in the plane subdrawing. And one case is that there exists a vertex which has degree at least d plus 1. And the other case is that there doesn't exist such a vertex. In case 1, we are going to look at this vertex of degree at least d plus 1 and as all the vertices it is connected with in this plane way that we got this degree. So we have the star vertex V and the other vertices. Now, this drawing is of the form that if we leave out the edge from V to the vertex with high degree, then we have a plane K2D. And it is known for any plane that K2 something, that if it's a subdrawing of a complete graph, then the part, the vertices on the bigger part of the bipartition, so the somethings, in our case the D vertices, induce a C-monotone drawing. So we have found a C-monotone drawing of the complete graph of D vertices, which are exactly the neighbors of our vertex with high degree. In the other case, if we don't have a vertex with degree at least d+1, then all vertices have degree at most d, meaning we have a d-array tree by definition. So this part of the proof we have also roughly shown. Meaning, what do we have in total now? We started with the simple drawing of a complete graph, and no matter which way we went, we know that we always end up with a plane path of a certain length. And the length is square root of d, or omega of square root of d, or omega of log n over log d. So we have the minimum of this we always can find. And this was for any d. If we choose d correctly, then we can, which in this case means we want to have log square of m, then we can show what we claimed in the beginning, that any simple drawing of the complete graph contains a plane path of length omega of log n over log n. Now for the remaining time, let's look at the second main theorem, and that is that any simple drawing of the complete graph contains omega of square root of n disjoint edges. A bit more precise, we're actually going to show a floor of square root of n over 48 edges. To do that, we take our simple drawing of the complete graph and take any maximal plane matching that we find. If it holds already this size, then fine, we're done. If it doesn't, then we're going to show that it contains a generalized twisted drawing. So let's do that. We start with our maximal plane matching, and in this figure you can see here, the matching are the black edges, and the vertices are colored now so that the matched vertices are recognizable as black vertices and the unmatched vertices are in red. Then we first extend this maximal plane matching to a maximally plane drawing of only the vertices that were matched. So we leave the unmatched vertices out for now and just extend the matching by edges. And now we again use the nice theorem we already used before, that any maximal plane subdrawing of a simple drawing of the complete graph is biconnected. So we know that what we have here is a biconnected plane subdrawing, and the vertices of this drawing are exactly this plane drawing are exactly the matched vertices, and the unmatched vertices are distributed somehow in the faces of this subdrawing. We don't know exactly how they are distributed. What we do know is that since this is plane with some planarity arguments by Euler and some counting, there is at least one face that has much more unmatched vertices inside the face than it has matched vertices on its boundary. And we will look at this face. And bottom left, you can now see the precise number of what is much more meant. But we are going to ignore precise numbers and just look at the main ideas. So we have this face now with matched vertices on the boundary with unmatched vertices inside, a lot of them. And then we will use another of my favorite theorems, which is that any simple drawing of the complete graph with at least 3 vertices that contains a connected plane subdrawing and a vertex which is not part of that connected plane subdrawing. Then it also contains 2 edges that are incident to that vertex not part of the plane subdrawing, such that these 2 edges could be added to the subdrawing, and then we get a bigger subdrawing which is still plane. And also the vertex V, the vertex that was before separated, is now connected with the plane subdrawing, and both edges are incident to it. And yes, and it's a plane matching, a plane drawing in total. So what this means for us is that we can choose any unmatched vertex inside this face, and we will find two edges that connect it to the boundary of the face, so that the boundary plus these two edges is something plane. Then if we choose another vertex, we can find two edges that we add again, and they are incident to that vertex, and the thing we get is plane, now including also the edges that we added before. If we remember that we started with a maximal plane matching, then we can see that these two edges we add always go to the boundary of the face. That's because if there were an edge going between two unmatched vertices inside the face, then actually we could have added it in the beginning to the matching. It would still be plane, it would be bigger, which is a contradiction to the maximality. So we can do this for every vertex inside the face, and actually we do end up doing this, and have every vertex connected with two edges with the boundary of the face. And the thing we get is plane. To see what this structure is a bit better, we can consider two edges that belong to one vertex as one long edge. If we do that with all these pairs of edges, we get lots of these long edges, and we still have something that is plane, but we have something that is not a drawing of a graph anymore, because there might be several edges that connect to two vertices on the boundary of the face. So we can bundle them and say, okay, this is now one big edge. If we do that for all, then we have an autoplane drawing. And with some planarity arguments, we can bound the number of diagonals, so the number of these big edges in the autoplane drawing. And then if we do some counting of how many unmatched vertices were original in the face, we will find that there is one big edge at least, where there are a lot of vertices belonging to it. So here that's the thing that would go from V to W. There are a lot of vertices connected with both. And we're going to look at them. Now, the first thing we notice is that, again, we have a plane drawing of K2 something, where we saw already before, well, said already before that, then these edges, which now are the vertices, sorry, which are now the red vertices, induce a C-monotone drawing. Just that now we are not satisfied with having a C-monotone drawing, we need a generalized twisted drawing. For that, we are going to look at the edge from V to W. And in this figure, I drew it outside completely of the face now. This doesn't always have to be the case. It could be part of the boundary. It could cross the boundary. Important thing that it cannot do is it can't, well, one thing is it can't cross anything adjacent to V or W. And the other thing is it also can't go in between these blue edges, because it can't lie completely inside the face. Because remember, this was the face of a maximally plane drawing on vertices where V and W were included. So we can't have an edge in there. And then we look at the edges between two of these red vertices. Now we said before, this edge cannot be completely inside the face, because that's a contradiction to the maximally plane matching we started with. So the edge has to cross the boundary of the face. And with that, it also has to cross the edge from V to W. This holds for all edges. So the edge from V to W is crossed by all edges of the drawing induced by the red vertices here. And this gives us a drawing which is essentially a generalized twisted drawing. To see that, we can see V as this origin point O from which all the rays went out, and any pair of edges belonging to one of the red vertices and going to V and W would be one ray that goes from V through the vertex to infinity. W is now symbolizing infinity. And the edge from V to W that crosses everything is the ray that goes out and crosses everything. And I forgot to look at the time. So if we want to draw it really like a generalized twisted drawing, we can draw it first on the sphere and then make a stereographic projection through V to actually get rays, but that's details that I think I don't have much time for. Important thing is we found something that is essentially a generalized twisted subdrawing and has this size. And since we know that generalized twisted drawings have plane Hamiltonian paths and therefore also plane matchings, we can have found a matching of this size, so square root of n over 48, meaning that we have shown that any simple drawing of the complete graph contains at least omega of square root of n disjoint edges. To sum up, any simple drawing of the, so we have shown two main theorems. The first one was that any simple drawing of the complete graph contains a plane path of length at least omega of log n over log n. How we did this was that we showed that it contains one of three things as subdrawings, either a generalized twisted drawing where we know we have a Hamiltonian path or that's plane, or a monotone drawing where we know that we have a plane Hamiltonian path, or a plane DRA3 where we know we find the path of the right length. And just now we talked about omega of square root of n disjoint edges in any simple drawing of the complete graph, where we started with a maximal plane matching, which either already had the correct size, or we find a generalized twisted drawing again, and with this, the disjoint edges. And that's what I wanted to talk to you about today. Thank you very much for listening. Are there any questions?
So anybody in the audience has questions? No? Okay, so I have a few questions. Mm-hmm. I found the talk very interesting, and something that I'm happy to see is that it's one of, it's like of the first times that I see that the structural theorems on plane drawings are being used to prove a result on drawings. So it's a collection of a lot of results that have been coming through the years, and this either or situation, right? Either you have this structure or you have this other structure. Is there a way of trying to make to have a similar approach to prove Harari-Hill's conjecture about the crossing number of the complete graph? Do you think that's even possible?
But the crossing number, maybe there is, but the one I haven't thought about this much, but the one difficulty that I see now in the difference is that for the plane drawings we look at, we really only need a substructure, and if the rest does stuff and crosses, we don't care. For the crossing number, we actually need a minimum. So what the rest does is very relevant, because if there appears a crossing somewhere not in our substructure, then that does change things. Which doesn't mean that the either or approach wouldn't work, but at least not exactly like this.
Yeah, because here you're looking for something local, no?
Yes.
Yes, and for the crossing number, we will need something that takes into account everything. So you will have to keep track of all substructures of this type, no?
Yeah, we can throw. So here we would take something, once we have it, we throw away the rest basically, and then we just focus on what we just found. And for Harari-Hill, I would guess we can never draw anything away, or at least one would need to be very careful.
And in the case of Harari, of cylindrical drawings, optimal cylindrical drawings, do you know how do they behave with these structures? I mean, do they have, say, both generalized twisted drawings or both monotone drawings, or do you have only one of the types? Do you know? Are they extremal in some sense with these substructures?
The hierarchical drawings, well, so the three listed C-monotone drawings are in a very hierarchical drawings.
Sorry?
Just that, so the what we define as C-monotone drawing is sometimes also called cylindrical. It's just, but we don't always have this geodesic thing.
Okay.
But we can have hill drawings, we can draw C-monotone. Okay. So this direction works. And about which part then is monotone and which part is generalized twist, I would guess that it's more on the monotone side. Also the extra parts like the top and the bottom extra are monotone.
All right. Yeah. Okay, okay. And also I noticed that your bound, there is a gap, no? Like you have a square root of d and log n over log d. And you choose d equals to log square of n. But it's just a matter of solving the equation for d, no?
Yes, so it could be slightly improved if we, okay, I can find it. If we choose the, so there is a better solution for d if we really do the derivative. But asymptotically, actually being smarter with d wouldn't be the solution. We would need something other than the d-array tree would be more, my guess. So it seems that the d-array tree is not the perfect opposite maybe, but not sure what else to use, but so it can be slightly improved if we choose a smarter d, but to really get improvement, we probably need to have something else than the d-array tree.
Yeah, I think it has a name. You sort of need the inverse of n log n, no, of d log d, sort of. And that thing has a name. Yeah, anyway. Okay. Oh, well, nice, very nice talk. Thank you. Anybody else in the audience? ¿Nadie tiene preguntas? ¿No? Ok. Bueno, pues le agradecemos a Alexandra. Gracias, Alexandra. Ok. Bueno, pues gracias a todos por su asistencia. Nos vemos mañana para la plática de Rosna. Okay.